Nicolas that has some problem with Zoom. I understand that the Zoom crashed down, so now he's ready for his presentation.
Yes.
About
Thank you. You should be able to hear me and see me.
Yes. We don't see the presentation. The title is Scalable Domain Decomposition Preconditioner for Cardiac Mechanics. Nicolas BARNAFI from University of Milan, but we still not see. Okay, now is we don't see you, but we see the presentation, so it's
okay, even better.
No. But if you is the only way to see the presentation, okay.
Yeah, it's fine. Okay, so thank you everyone for coming here. I'll be talking about efficient solvers for cardiac mechanics. I'd say the main motivation for this is the rich landscape that we can see in technology, and particularly in the last years. So I have been usually exposed to doing parallelism for these kind of problems on clusters running 64-bit Intel processors. And this is, of course, not the big picture. We know that machine learning algorithms leverage the massive parallelism available in GPU devices. And there are some other competitors, such as the ARM processors that now Apple came up with on their own, inspired by mobile processors. And then Intel's coming up with options. So there's a really rich environment of hardware that we need to be using, where of course the hardware itself does nothing. So that's where we need to run our algorithms so that we get the best performance out of them. But still, it can get really confusing, right? There are many aspects about this. There's the compiler has an impact on performance. We need to see how we use our linear algebra, in particular our matrix operations. And there are many options. Ones that use the GPUs, it's NVIDIA, AMG. On top of them, we have many linear algebra options. This Jingo library is quite recent, and it's a nice alternative that it's more fluent with respect to the kind of device that you're using, and also the kernel. So I'm mentioning in particular these ones because Clear Linux is a new one that Intel came up with. Rocket Linux is kind of the successor of CentOS, and my kernel is the one that they use in the Japanese top one supercomputer. It's a kind of microkernel that's being used in the distributed nodes that are not used for logging or anything. So we see that the picture is really complex, and this all of this to be able to use good software to give nice scalability and to use the say the hardware for the adequate scenario. So in particular, we'll be looking at domain decompositions that look as a nice option to kind of take advantage of all the options. I'll be talking about it for cardiac mechanics in particular. This is, of course, not the only option, but this is where we're focusing, as nonlinear mechanics is a very difficult problem. The domain decomposition solver that we'll be focusing on is the BDDC. It stands for balanced domain decomposition by constraints, and some numerical tests on it. And finally, I wanted to close with giving a small, let's say, questioning the gold standard of using a Newton method that we have discovered that can be outpowered with some effort. So really super fast overview of cardiac mechanics only for the ones who haven't seen the equations that I guess that 99% of the people here have. But for those who haven't, we have a problem where we're looking for a displacement D that solves this partial differential equation. P is called the Piola stress tensor, and it stands for the mechanic response of the tissue, and P active represents the stress generated by the contraction of the cardiomyocytes. This can get really complex, so I'll just give you two aspects that are fundamental here. It's the boundary conditions have to consider the pressure inside the tissue given by blood, okay? And there's a boundary condition on the outside that takes into account the friction with the pericardium. And that's it. That's cardiac mechanics in a nutshell. We're looking for a displacement that gives a response like this one here. And to solve this problem, the usual flow that we use is a Newton method, right? So it's a root finding problem that actually comes from an optimization problem. We write this thing as a residual equals to 0. When we linearize it, meaning that we use Taylor's approximation, first order, we get a matrix called a Jacobian matrix, and we try to compute this increment. We compute many increments until we see that this thing stabilizes according to a certain error criterion. And this is, of course, expensive. Still, it's really good. It has quadratic convergence usually if you're close to the solution, if you start close to the solution, but it requires reassembling this matrix at each iteration, and you have to invert it. So it's a difficult problem. It requires good preconditioner for the use of iterative methods. Okay, that's the setting where we're moving. We'll be using 3 kind of benchmarks that are available here. I saw there's a presentation about benchmarks in a little while, so I'll be really interested in that. In the meantime, I'll be using these 3 ones, which is a beam, a swelling test, and a contraction test with the pressure in the inside, which is the most challenging usually. Okay, that's all for cardiac mechanics. So how does this preconditioner work? And I'll try to simplify it as much as possible, only to the main issues. So when we do parallelism, there's a piece of domain that goes to each process. So that here, for instance, we'll be using 3 processors to solve a problem in this circle. And substructuring domain decomposition methods basically consists in solving the problem that corresponds to each domain independently, and then you put them together somehow. There are many technical issues about them. So how do you put the solutions together after a while? So you have to kind of average them in a certain sense. What's going to happen with this domain here? So it's not with omega 1 is not in contact with boundary conditions at any point. So it's going to be a floating domain that you'll have to take care of regarding the kernel and other numerical problems. So this kind of methods known as the balanced domain decomposition by constraints, what it does is that it balances this, of course, with constraints, which are continuity along certain degrees of freedom. Usually you can start with vertices. So you see here that the vertices where these domains intersect are continuous in this case. And this, of course, this makes use of the capacity that these kind of preconditioners have of preserving the complexity of the problem locally, but then you avoid many of the little details, as I was mentioning before. And we'll be interested in this because they have really beautiful properties, such as this one, that your preconditioned system of equations, at least in linear problems such as linear elasticity, can be proven to enjoy this beautiful quasi-optimal conditioning, where this is actually the ratio between the diameter of the domain and the mesh size. So if you actually keep this number constant, as in weak scaling, this is theoretically constant. So this is a really nice result and motivation. And there are basically 3 tuning knobs that we're looking at. So what are these degrees of freedom where we impose the continuities? The standard ones are the vertices, the averages on the edges, and the average on the faces. On each subdomain, the best option is to use just direct solver, where there's a lot of software available, and we have tested that as well. And initialization is a big problem, as many of you might have seen in algebraic multigrid, and this is something that we have already performed in LifeX. So for those of you who went to the workshop in the morning, you'll be happy to see that this has already been done, and it can be seen through these really simple statements. We can set how many degrees of freedom each point has, who are this is called the near null space, that in algebraic multigrid is important, and here as well. So there are many parallels between domain decomposition methods and algebraic multigrid. And finally, this is a new one, and you need to state who are the coordinates of your domain to get a better definition of the vertices. So having done this, for instance, we can see what's happening if we change our degrees of freedom. If we use only the edges, second order doesn't converge. The best alternative we're seeing is using edges and faces. And we see that if we add the vertices, the change isn't substantial. So in practice, keeping edges and faces is the best option. And you see here that for first and second degree, we get really similar iteration counts. This can be intuitively seen by the reduction of complexity that this kind of preconditioners have, and it's a great advantage. You wouldn't dream about this, for instance, with an algebraic multigrid. The difference in software you use for your direct solution is kind of surprisingly different, and the takeaway message is that you should use MUMPs. So for local subdomains, it sometimes isn't the best. So here it gets beaten by Intel, here it gets beaten by Super LU, but here also Intel didn't work and it has some kind of error message. And Super LU here works much worse. And in the parallel LU, you see how MUMPs really outperforms everyone. So, and MUMPs also supports using a Cholesky, parallel Cholesky. So there's nothing to do here. MUMPs is the best option. And finally, of course, some scalabilities. So this is with the benchmarks I was mentioning. And what you should note here is that when you double the number of CPUs, you see the time we take being reduced by half, with a really small increase in the iteration counts. This holds for all of our test cases. This is for 1 million degrees of freedom, which is already a big problem in mechanics. For second order finite elements, you'd see basically the same behavior. It looks as if I didn't change the slide, but then if you put one next to the other one, you'd see that behaviors are really similar. Iteration counts are really similar, and then you just see time increase due to the use of second order elements. So this is a really good result, and this meaning that this is really well suited for let's say massively parallel machines, and it's kind of the motivations for developing these kind of preconditioners. And this we're actually waiting for the Challenge supercomputer to release its new machine to do our super large tests. But here are some preliminary tests we did some time ago on the beam, and you see that it still goes up, right? Like we go up to more than 200 degrees CPUs, sorry, with this kind of time halving, first order, second order, and weak scaling performs almost good. There's a slight worsening with the increased degrees of freedom, even though the iteration count remains low. This is due to the conditioning property that I mentioned before. But this has already been observed in literature for structured grids, and this is actually some cases that we have seen also in unstructured grids. So it's it should work okay. I wanted to close with kind of questioning the nonlinear solver, and these are preliminary results. But I think that nevertheless they're super encouraging. This study is anyway almost complete. So we use Newton because it gives second order convergence. It uses usually a really low number of iterations, or it just doesn't converge, and this comes at the price of being expensive, right? You have to reassemble and invert your problem many times. So after some attempts at using first order methods for the mechanics, we saw that this wasn't an alternative. There's kind of a midway solution called the BFGS solver. It's a quasi-Newton where when you use your Taylor approximation, you consider an approximation of your Jacobian here that we're calling this B matrix. Okay, and the great thing is that when you go through the iterations of this method, you can enrich this matrix by using the previous iterations. So there's no reassembly of the matrix. You consider only one approximation, and then you can go on with solving it. And we have actually seen that if you use an adequate initial guess of who this matrix is going to be, you will get nice behaviors such as this one, the iteration counts remain more or less fixed. For a small problem, time improves, of course, because this is a great problem. You only have to invert this small approximation, and then you'll just get vector-vector products here. So it should be really cheap to do. Also, with a little bit of a bigger problem, this is always cardiac mechanics, and this is really nice how again you can double your CPUs and you get a halving of your solution times. And of course, how does it fare against Newton? This is a supernatural question, and it fares greatly. So we did the same thing. We considered a regularly sized mechanics problem, and doubling CPUs, we see that this performs better and better with time. So let me conclude. We have talked about domain decompositions. They kind of preserve complexity of the problem. In particular, the BDDC, it performs adequately here in cardiac mechanics, and we can improve Newton solvers. This holds, in particular, for these two techniques that we have seen. It seems really promising to then go for GPU accelerated scientific computing. I just finished my 15 minutes, and I wanted to say that I will only receive nice questions. Today is my birthday, so it just got your card just got laminated. Thank you very much. I'll be happy to answer your questions.
Thank you, Nicolas, and of course, good birthday. And how old? You have to say the age now.
Yeah, it's only 30.
Okay, so it's a very important birthday. Okay, yeah, congratulations. And Elias, please, with a nice question for Nicolas.
I hope so. First of all, also happy birthday from my side. Great talk. Just for clarification, when you wrote CPUs, did you mean by that like the MPI processes? Or did you use like multiple processes per CPU?
Sorry, it got froze. Can you repeat? I removed the video.
Okay.
My question was like in your the scalability, you wrote like CPUs, 32, and so on. Was this like MPI processes or? Mm-hmm. Okay.
Yes, this is all MPI parallelization.
I mean, like you have 32 CPUs, but I don't think these are single core CPUs, or so. I guess each CPU will have, I don't know how many cores. I hope I didn't confuse you. No?
All of these tests were done in a, to be precise, all of these tests were run in a single high performance node. Each of the CPUs has 2 threads, but I consider only 1 thread for parallelization. I usually don't see much of an improvement making use of both threads in each CPU. So I would usually do parallelization tests, in particular these kind of tests with only 1 thread per CPU. So those 32 is only 1 thread per CPU in a single node.
Okay, thanks. Can I ask a second question about the last?
Yes, I don't see other questions from the audience, so please, Elias.
About the Newton, did you like think of comparing like a textbook Newton with there like other tricks you could do, like Jacobi freezing and I don't know, introduce time dependence? Then you can also get.
Yes, that's a great idea. We have been trying, for instance, to lag the Newton as maybe you have seen as an option in PETSI, but it doesn't perform greatly. These are tests that I've been trying to complement with, say, Anderson acceleration. So you always have the option of using line search for that, right? Mm-hmm. But line search in this kind of case is a little bit it adds a little bit of overhead, and it doesn't give such big improvement in iteration counts. I've seen better results using Anderson acceleration in this kind of let's say relaxed Newton schemes, but still I have seen the BFGS obtain better performance if you use an adequate approximation for your initial Jacobian.
Okay, thanks.
Yeah, no worries. Thank you for the questions.
Thank you, Elias. And I think we can thank Nicolas for his talk, and happy birthday again.
Thank you very much. And thank you all for your attention.